Huh?
That's for my wife's out of town.
You said.
How about you? Nothing? Absolutely nothing.
I'll be breathing and living, but yeah, really nothing.
Sounds good. I like boring. Does anyone have any homework questions?
I has a homework question.
You do.
What's that? 3.2,
Okay.
16 or 17.
Yeah, like
We're on the same
I
topic.
don't know how to sleep right now.
Was this the perpendicular?
Perpendicular line, yeah. Utterly confused.
All right. Yeah. So it says the line that's perpendicular to the tangent line is called the normal line. So it says find in the equation line, or does it say, yeah, okay. Find an equation of the line perpendicular to the line that is tangent to the following curve at the given point. So then, they're looking for the equation of the normal line is blah, blah, blah. So really it just boils down to, can you find the slope of the tangent, or can you find the equation of the tangent line? And then you construct a line perpendicular to your tangent line. Right, so that's probably a long lost algebra thing. What's true about perpendicular lines?
They're like, when they cross, they make 4 right angles.
Yeah, so they cross at a right angle. The slopes are reciprocal and negative. Negative reciprocal gives you a perpendicular line. You've got to find the Y-intercept for the perpendicular line because it's not the same. It's not the same as the given line. So if you say, I don't know, for whatever reason, let's just say this is my 3x plus 1 is the tangent line, then what's the line that's perpendicular to this? And I guess I should give a point, but line that is perpendicular to 3x plus 1. The point is given, so we'll just say we've got a point on this line that's at 0, 1. So you just say, well, the new line, we'll call that y2. The new line that's perpendicular to y1 has a slope of negative 1/3, and we know that if we want it to pass through this point, then okay, we'll say it passes through this point 0, 1. So then you just got another point slope formula for that after you've, okay, well here's my slope, here's my point.
Oh.
I don't know what happened there.
Okay.
So yeah, then it's just another equation of the line you have to write. But the key to that is remembering how do you construct a perpendicular line. The slope is negative reciprocal of whatever other line you're dealing with. Does that make sense?
That was the part that I was confused.
Okay.
This is how to get from your line to your normal line.
Okay, yeah.
That was the part that was like.
Yeah, so they do give you this point, the normal line at the point 2, 2. So again, you find the tangent line at 2, 2, and then you have the slope of your tangent lines negative reciprocal and the point 2, 2 into the new y minus y1 equals m, etc. Does that make sense? Is that clear?
No.
Okay, yeah. So, yeah, any other questions on?
I've got one, but it's from 3.3, and we may actually cover it today, so
Okay.
I can hold off.
And hold off then?
Yeah.
Okay. All right, other questions on the homework? guess it disappeared. So we left off in section 3.3. Particular example we were working on had us find the equation of the tangent line on the function 2x minus 1/2 e to the x at the point 0, negative 1/2, which we did. And then we want to find the point or points on f of x where the tangent line is horizontal. So we went through the derivative to find the slope of the tangent line at any given point, or any given x value rather, and we applied our shortcut to find f prime was 2 minus 1/2 e to the x. And then since we wanted the tangent line at the point 0, negative 1/2, we just plugged 0 into our derivative to get the slope at that location, which was 3/2. And so we came up with the equation of tangent line. Was everybody okay with that? Were there any questions on how we got what we got? Okay, so we'll start part B. How do we want to say that? I forget the question exactly. Where f of x, the tangent line is horizontal. Points on f of x where the tangent line is horizontal. So then the question arises, how do we find the points on the graph where the tangent line is horizontal? Or what does it mean to have a horizontal tangent line? What? Peaks? Yeah, the peaks and troughs of like polynomials and such will have horizontal tangent lines of the derivative. Yeah, so horizontal tangents correspond to x-intercepts on the graph of the derivative, right? But how do we actually find them?
We can set our derivative to equal.
Right. So isn't the tangent line, the slope of the tangent line, described by the derivative? So when we say, all right, well, what x values is the slope of the tangent line horizontal? The horizontal slope is 0. So when is the first derivative equal to 0? That's how we find, on any function you're given, if they ever ask, where does it have a horizontal tangent line? You have to take your derivative and set it equal to 0 and solve for x. So our derivative was 2 minus 1/2 e to the x, and we want to know, where does our derivative equal 0? Where is the slope of the tangent line horizontal? So this is a lot more frequent in chapter 4, where we take our derivative and then we solve where the derivative is equal to 0.
Maybe like ln of -4?
Close, super close. Remember, the natural log is not defined for negative numbers. So we would say that happens when 2 is equal to 1/2 e to the x, maybe, because there's a couple of ways to look at this. Or when 4 is equal to e to the x. So when does e to the x equal to 4?
The natural log of 4.
The natural log of 4, not negative 4. That's the only x value we get out of that equation. So that is the only place that our original function has a horizontal tangent.
So that y equals equation, that's just the general slope?
The one we wrote up here,
Yeah.
that one, that's just the tangent line itself at that point. Another way to say that is if I said to find the tangent line on the given function when x is ln4, then you would come up with the slope is 0.
So what's the point of finding that?
The-
y equals, that y equals equation? Is there like something more that we'll do with it in later sections?
Yeah, so the line, for most things we do, the line is more of a mathematical thing, just to come up with that line. Maybe when you get into like Calc 3, you'll start to do stuff with the actual line itself, but they're actually planes. So
Okay.
we don't really do too much outside of just writing the equation of the line,
Okay,
just for math purposes, I guess.
okay.
Usually in physical applications, you want to know what was the instantaneous rate of change in temperature at a particular time. You would just be after the slope at that point, because that is the rate of change. The instantaneous rate of change at that point is 3/2.
Okay.
So yeah, usually we're referring more to in physical context, you're referring more to the slope of the tangent line than you are to the equation of the tangent line.
So finding something at a particular point of x, we're going to be using the derivative, not the y equals.
It really depends on the question. If the question's asking where at on the function does a certain thing happen, then you want to make sure you're going back to the function. But a lot of times that does involve us answering a question about the derivative first. So like when does this, when you see this graph in green was our, let me write this here. This was the original function that was given to us. So looking at that graph, and if we say, where does that graph have a horizontal tangent? Visually you can see that the horizontal tangent's here. But where does that actually occur? Well, we have to look at the derivative of the function, not the function itself. So we look at the derivative and say, well, on the derivative is 0 at x equals to ln4. Therefore, the original function has a horizontal tangent at ln4. So it really depends on what the question's asking.
Okay.
But most of the time you are you are answering questions about the original function given. All right, so let's write that out then. At x equals to ln4, f of x has a horizontal tangent. So make sure that we're talking about f of x as a horizontal tangent. And our instructions were to identify the points on the function. Here we have just the x value. So we know on f of x at that x location we have a horizontal tangent, but the point, as we all know, is xy. Again, we're referring back to the original function when we plug that in. Because it didn't ask for points on the derivative, it asked for points on f of x.
So we don't necessarily need to solve for y, we just know that y is represented by the function at ln of natural log 4.
Yeah. Yeah, and make sure that we're plugging that into the original function, not the equation of our tangent line.
By original function, you mean the true original or the derivative?
Yeah, the f of x that we started with. So that would be 2 times ln4 minus 1/2 e to the ln4. So I guess we could get like approximate values or just leave them exact. And then negative 1/2 times e to the ln of 4 is negative 1/2 times 4, which is negative 2. So we can plug those in to find them approximately. If we need to. So that's the point on the original function f of x. So let's go ahead and graph that again. See what ln 4 is, about 1.386. So we'll have 2x minus 1/2 e to the x. See what horizontal tangent is here. So we identified that location of x as 1.386 or ln 4, and then we get 2 ln 4 minus 2 for that 0.773. So we'll write that here. Any questions about that? It's somewhat common in chapter 3 to find horizontal tangents, but it is, at least for a large 3 or 4 sections of chapter 4, it's a lot more prevalent. It's almost in every single question that we look at. Because in chapter 4, we move to like what derivatives can do for us. And so it could refine some of our graphing techniques when we start talking about derivatives. Namely, one of them is locating the local minimums and local maximums of any given function. So identifying where your function has a peak or a valley, your local min or local max, you have to find the derivative and you have to solve the equation when is the derivative equal to 0 to find those. So it's not something you should soon forget. Okay then, everybody all right with this? We're gonna move on. So a couple of derivatives to find here. What's the derivative of e cubed?
0.
What kind of function is e cubed?
Constant function.
It's constant, right? It doesn't have an x, it doesn't have a variable in it. E cubed never varies, it's always flat.
Just e cubed.
No, the derivative of e cubed is 0 because e cubed is a constant.
So what's theorem 3.6 referring to then? In the previous theorems that we
Yeah.
looked at, that theorem for 3.6, the derivative of e to the power of x.
That's for e to the power of any x.
Yeah.
E to the power of an actual number is just a number raised to the power of another number. So it's just 2 point whatever times itself 3 times, which is just a number. A derivative of any number, of any constant number is 0.
Yeah. The quick way to check, I'm taking the derivative with respect to the variable x. Does e cubed have the variable x? No, it doesn't have the variable x. It's a constant with respect to x. The reason that's different is this is e to the x power. So that's varying. That could be whatever we specify it to be as soon as we plug a number in, but we haven't plugged a number in. So this is something that varies. This is something that is constant. Okay. So, yeah, I'm gonna write this here too. So as long as you don't see, like, if you just got to be mindful, I'm taking the derivative with respect to what variable. Is it x? Usually it is x. Is it t? Is it w? Is it s? If I don't see those variables in there, then that automatically constitutes that thing as a constant. So, you know, I don't know, a little bit more abstractly, we could say, what's the derivative with respect to w of 2x squared? 0. There's no w in there. 2x squared is constant with respect to w in our you know, sort of 1-2 dimensional setting. But I think that's the easiest way to tell, but I don't think that's the most technical way. More technically, you should know when you're dealing with a constant versus something that varies. Okay, how about example 2, square root of x over 3?
-1/6 x to the power of 3 halves.
Negative 1/6 x to the power of 3 halves. Okay.
Negative 3 halves, excuse me.
3 halves.
Negative 3 halves.
So what rule are you using to take the derivative then of number 2?
The numbers I couldn't tell you. What I did is I took 1/3 out, so I separated, essentially set the derivative of 1/3 times the square root of x.
Okay.
And then put the square root of x inside the parentheses and turn the square root of x into the negative 1/2 x to the power of negative 1/2 minus 1.
Okay. Yeah, that's exactly how we want to look at that. It's just a constant, 1/3 times a function of x. So the constant gets pulled out to multiply. And I think also there's a discrepancy there sometimes when we look at it. If the derivative of a constant is 0, then how come the derivative of 1/3 times root x is not 0? So there's two distinct things happening there. Either you're taking the derivative of a constant by itself, or it's a constant times a function of x. So here is the latter. Constant times a function of x, the constant just gets pulled out to multiply. Okay, and then we have the power rule for x to the 1/2. Yeah, okay. So we have 1/3, the power comes down to multiply x to the 1 less power. So we have 1/2 minus 1, which is minus 1/2 power. Sorry. Yeah.
That'd be
halves.
the end result. Anyway,
Yeah. So that's basically
on
it.
the exponent, and then I just multiply 1/3 times 1/2.
Right. Yeah. And then we can reconcile the constants. We have 1/6
Got the 1/6 x.
x to the negative 1/2. Yep. Okay. Does anyone have any questions on example 2? Okay. How about example 3? You're right. Yeah. So we look at this. Hopefully you can see that's a product of two functions of x. We have yet to talk about the product rule. Once we do, then you can apply a product rule to take the derivative. But we haven't talked about that yet.
Did you just solve them separately?
Well, so that's the thing we haven't talked about. The derivative of a product isn't the product of derivatives. So the derivative operator doesn't distribute across products.
Or I guess more so like I wouldn't even think about distributing it. I would just solve this derivative of square root of x and the derivative of x minus 1.
Yeah, so you couldn't do that. I couldn't take the derivative of root x and multiply it by the derivative of x minus 1. So the product rule doesn't work that way for derivatives.
Isn't it derivative of the first time, or times the second one, and then derivative of the second times the first one?
Right, yeah, but we don't know that yet. That's in 3.4. So I will say that whether we have this arsenal of derivative rules or not, if you can simplify the function before you take a derivative, it's always going to be simpler to take the derivative, right? Because you're dealing with a simpler function. So, as was suggested, what we should do before we take the derivative of this, even if I knew the product rule, before I take the derivative, let me just distribute and simplify this function, and just so I'll have powers of x. So what's the square root of x times x?
X square root of x.
X to 1 half.
Yeah, so it's, well, it's x times the square root of x, but what is x times the square root of x? It's x times x to the 1/2. So it's x to the what power? To the 3/2. Yeah, you add the exponents, 1/2 plus 1. And then root x times -1 is just negative root x. Keeping in mind, we're going to take the derivative of that, so it's more beneficial to write those out as powers. So we're going to use the power rule. We distribute equal representation of f of x. It's more conducive to take the derivative. So power comes down, multiplies x, we take 1 away from the power. Derivative of x to the 3/2 is 3/2 x to the 1/2. And we'll do the same thing over here. So that's our derivative. Any questions on that? Okay, how about example 4, x cubed minus x over x?
I feel like you need to,
Factor in x.
yeah, or you would at least need to break those apart into 2 separate fractions.
Yeah.
Because if you leave it as is, you're going to have a 0 in your denominator.
Yeah, and also the fact that the derivative of a quotient isn't the derivative of the top divided by the derivative of the bottom either. So again, even if we have the quotient rule for derivatives, it's much more efficient to simplify the function first, so we can either factor an x out of the top and then cancel it with the x on the bottom, or we can split this up. Either way we approach this, we'll end up with the same result. So f of x is equivalent to x squared minus 1. Just make a note that we can't divide through by 0 because the original function is not defined at 0.
2x for the final answer.
So the derivative of f of x, which simplifies to x squared minus 1, is just 2x. Derivative of x squared is 2x. The derivative of -1, it's a constant, so that is 0. So if you want to look at it like that initially, that's fine. But it's just 2x. Yeah. Okay. How about example 5?
From the top is the difference of squares, so we can factor it out with x minus 1.
Yeah. So we're going to factor this first, or yeah, whatever. Difference of squares on top over x minus 1. So our function simplifies to x plus 1. And the derivative of that is just 1. Yeah. derivative of x is 1, the derivative of the positive 1 is 0. So simplify if you can. Before you take the derivative, you'll end up with a simpler function to deal with, which means you have a simpler derivative. Here we should note that x can't be equal to 1. All right. That's really the purpose of those exercises, just to kind of highlight. You don't have to take the derivative of the function as it's presented to you. You can simplify first and then take the derivative. Since we're pressed for time, I'm going to skip these two examples. They're similar to that first example that we looked at. These two, all we're doing is writing out the equation of the tangent line. So if you do want to revisit these, I'll go ahead and write the answer so you can check if you want. Equation of the tangent line here for this one. Y equals to negative 6x. Negative 6 minus 1 plus 5. So then, example 2, equation of the tangent line, y equals to negative 3/4 x plus 1/4. So at any point, some of these ones that we just glance over on our notes, if you work them and you have issues, I'm happy to talk about them in class. It's just that we're a little bit behind, so we kind of need to speed up. So if you have any issues with those, please let me know, and we'll look at them. We can take higher order derivatives, meaning we can take the second derivative, the third derivative, the fourth derivative, assuming the function has a continuous derivative. But all we mean by higher order derivatives is, for instance, if I say take the second derivative, that means take the derivative of the derivative. So for us, it's primarily we're focusing on the first and second derivative in this class. Here in chapter 3, we see that the application of first and second derivatives are related to position, velocity, and acceleration. And more of, in a mathematical sense, I guess, first and second derivatives are related to the shape of a graph. I'm not well versed in the field of physics, but I know that you can go up to the fifth derivative when you talk about position, velocity, acceleration, and then the derivative of acceleration would be the fourth derivative, and that gives you your jerk. The derivative of jerk, which would be the fifth derivative, is snap. So you do have physical connotations to higher order derivatives. I just don't know all of them, but there are some. Primarily for us, though, we stick with the first and second derivatives in this class. Okay. So the nth derivative of a function just means we're taking the derivative of the previous derivative. I don't know. So the 10th derivative of x just says take the derivative of the 9th derivative. Okay, so for example, let's find f prime, f double prime, the second derivative, and third derivative for the function, I don't know, let's just do the square root of x. So like we mentioned last time, if you see any radicals involved, you just want to think about them as their corresponding powers in order to take the derivative. We've seen the first derivative as 1/2 x to the negative 1/2. Or, you know, we wrote that in another way. We said that's 1 over 2 root x. But leaving it how we wrote it as 1/2 x to the negative 1/2, keeping in mind we're taking other derivatives, would be a little bit more advantageous for us. Okay, so the second derivative, f double prime, is equal to the derivative of the first derivative. So what is the derivative of 1/2 x to the negative 1/2? Say that again, 1/4
To the negative 3/2.
times x to the negative 3/2. What do y'all think?
Shouldn't it be
Should be
negative
negative
1/4?
1/4.
Negative 1/4?
Yes.
Yeah, because the negative 1/2 comes out front to multiply the positive 1/2. Yeah, there's our second derivative.
Oh, so we're basically just doing the steps again on that derivative?
Yeah, exactly.
That makes sense.
Yeah. So yeah, it's if we have to take the derivative of the first derivative is just a constant times another power of x. So the power rule we apply again to get the second derivative. And the third derivative, you can write it like this. Typically after 3 though, we'll just do this so you don't have all of these primes floating around. But the third derivative is the derivative of this previous derivative. So what's the derivative of the second derivative?
3/8x to the negative.
Yeah. So we have negative 3/2 comes out front to multiply the negative 1/4. So we have a positive 3 over 8 x to the 1 less power. So negative 3/2 minus 1 gives us negative 5/2. So that's our third derivative. All right. Any questions on that? So as you get more and more rules, things get more and more complicated, right? I can say, once we have the quotient rule and the product rule, what's the derivative of a function that consists of a quotient and a product? And you've got 2 different derivative rules showing up to take the derivative of a single function, right? So you can imagine that these things can get very complex. You know, that's why I think it's, like I said, it's super important to stay on top of the derivative rules and get as much homework done as you can, I think is going to be crucial. So like if you not that you ever saw a crazy function, but what if I had sine of e to the x over cosine x times the square root of x plus 4? We have to talk about rules so that we can take the derivative of any function, right? So a function like this consists of a product, a quotient, and a composition of 2 functions on top, right? So you've got 3 different derivative rules in that one function that you have to apply. So that's what I mean by this, the derivative stuff starts to snowball as soon as we get into the next section. It really just starts compounding. So note cards, flashcards, whatever, you've got to stay on top of this stuff. Otherwise it'll bury you. Okay, that's the end of 3.3 then. We'll start with 3.4. And in 3.4 we get the product and the quotient rule. So the product rule simply says, how do we take the derivative of one function of x times another function of x? We already sort of alluded to this, but we'll use a couple of functions specific to motivate this. So let's consider f of x to be x squared and g of x to be x to the fifth. So I guess the main question here is, how do we take the derivative of the product f times g?
Would you find the derivative of them singly and then multiply?
Yeah, so we can say that the derivative of their product, just write this out, that's the derivative of f times g. So certainly, at this point, I don't know how to take the derivative of the product as a separate kind of thing, but since they're similar, I can multiply them out just algebraically and say that's the same thing as taking the derivative of x to the seventh. Right? Hopefully no one disagrees with that. And we know the derivative of x to the seventh is 7x to the sixth. So, I mean, that's the derivative of the product f times g. But typically, what we might look at that and say, well, you know, could I, instead of just looking at it that way, could I just take the product, or could I take the derivative of f and the derivative of g, and then just multiply their derivatives together? No, and again, we're using this example to show that it doesn't always hold. So it does, you know, it's not something we stick with. So, you know, our question really is, symbolically, can I take the derivative of f times g? Which again, for this example, we know is 7x to the sixth. Is that the same thing as taking the derivative of f and then multiplying that by the derivative of g? So we'll just compare this. This was our 7x to the sixth for this one. The derivative of f as by itself is 2x. The derivative of g was 5x to the fourth w. And so that's equal to 10x to the fifth. So here's the product of their derivatives, but here is the derivative of the product, which we know to be algebraically consistent, right? So we see that these two things are not equal. In other words, you just can't take the derivative of a product by taking the product, the derivative of each function, and then multiplying that together. So then that's why we have the product rule. How do we take the derivative of a product, f times g? We take it in this manner here. So it's f prime times g plus f times g prime. I guess usually the way we state this, let's call f the first or the first factor, I guess, and then g is the second. So we say the derivative of the product is the first times the derivative, I'll just capital D for derivative, first times the derivative of the second plus the second function times the derivative of the first. So since it's addition, it doesn't matter how you order those two terms. We could say f prime g plus f g prime, or you could say g prime f plus f prime g. All right, so let's look at a few examples of that. So let's find the derivative of x times e to the x. And I did mention last time too, it's really helpful if you can identify like the overall structure of the function, because a lot of these functions get pretty messy in how they're presented. So hopefully you can recognize this is a product of two functions of x that I can't combine. Like our last example, when I had the product of these two functions of x, they're like terms, so I can combine them, right? So really, algebraically, that thing right here is not a product rule, in effect. But x e to the x is, because there's nothing you could do to simplify that. So it doesn't matter which one you call the first and which one you call the second. It's totally arbitrary. This function could have been easily presented as e to the power of x times x, at which point you might say, well, e to the x is the first, x is the second. If we look at x e to the x, then we say, well, x is first and e to the x is second. The derivative rule that applies to either representation. So it matters how you set it up initially. What you're going to call the first matters. So, and the second matters. So just keep that consistent through your derivative process. So the derivative then of that product is the first times the derivative of the second plus the second times the derivative of the first. So we'll see three primary derivative rules: the product rule, the quotient rule, and the chain rule. And those derivative rules also involve additional derivatives. I would highly recommend that you write these out. Like if you're saying this in your head, first times the derivative of the second plus the second times the derivative of the first, which hopefully you are, every time you say derivative to yourself or in your head, literally write down that operation. Don't try to take the derivative as you say it in your head and just put that thing there. I promise it'll be a lot more efficient when we get to more complicated functions. So I said first times the derivative of the second. I'm going to explicitly write that out. I'm not going to compute that. Even though this one here is pretty straightforward, I'm going to write that out. Plus the second times the derivative of the first. I'm not going to compute that either. I'm going to write it out. If you're getting a lot of these right and you feel comfortable with just doing that, then please do that. But I promise as the functions get more complex, it's going to be super hard for you to tell when to stop taking derivatives if you don't write that stuff down. So I would develop this habit early. So since we have additional derivatives, we're not going to say that's the derivative. It's like you can't solve for x and still have x's on the other side, right? You can't say that's the derivative and still have derivatives left to take. So we still have to complete this. The derivative of e to the x is e to the x, and the derivative of x is 1.
So the order of the sum is not important.
No.
You can write it, like in that case, you just wrote it the opposite of the way that it's given in the example.
Right,
Or in
exactly.
In the equation.
In the theorem. Yeah, so we wrote this the opposite way the theorem said. Because they're saying take the second times the derivative of the first plus the first times the derivative of the second. But it doesn't matter because A plus B is equal to B plus A. So yeah, it doesn't matter. Of course, if you have negative signs coming out of the derivatives or the functions, then you just want to keep them where they are. But that order doesn't matter. All right, so that's our derivative, x e to the x plus e to the x. Any questions on that? Yeah.
Could you factor out the e to the x so that way it's e to the x times x plus 1, or is that not helpful at all?
Yeah, it is actually helpful. Initially, especially in chapter 3, when we're just primarily focusing on taking derivatives, a lot of the questions on the exam will say find the derivative but don't simplify. Because various problems have various ways you can simplify it. It makes it hard for me to grade, number one. Number two, it's primarily do we know how to take a derivative at this point? But I will say in chapter 4, being able to simplify the derivative is crucial when you have to determine where the derivative is equal to 0. So we could take out the greatest common factor in our derivative and write it like this. And our factored version, if you will, is more conducive to solving where does the derivative equal 0, or where do we have a horizontal tangent. This one's more conducive to solving that an equation. Right now we don't care where it's equal to 0. We're just looking at the derivative itself. Any other questions on that? So that's our derivative. If it said find the equation of the tangent line on the function x e to the x, we first find the derivative, plug the x into the derivative, then that gives us the slope of the tangent line, and then we write the equation, right? So sometimes that gets lost because we primarily focus on how do we take a derivative in this chapter, but we still have all of those other things we can do. We just don't usually do that a lot. Okay, how about 4e to the x times the square root of x? I'll give you all a minute. Well, I'll give you about 4 minutes to do that one.
that way you have like it feels weird, doesn't it? Yeah, it may not work at all. But I think this is legit. Because you're literally just taking out multiplication. Actually, apparently, that one is which is yeah. 4 e to the x times the square root of x plus 4 e to the Yeah, we were thinking this right now. I think so.
But I don't know, that's 2x to the negative 1 dx plus 4 dx x to the 1.
Because I'm just that's what I did. And then most likely, yeah, switch the kid.
No, I didn't.
I'm just trying to figure out.
Well, no, I didn't do that. I did the same one as this, which I was.
Oh, right, because that's the,
Yeah, that's the
derivative.
Yeah, so that's that.
This is all right.
Yeah, that makes sense.
Let me show you.
What? Where is it?
Double majored in bio.
Instead of biochemistry, she's like biochemistry.
I think so. I don't know. I know she took both of them.
I'm a,
I'm
not sure what direction it could go. I'm not sure if it's going from here to here.
Can she tutor?
I think
I'm trying.
It's like, just
and that is
while you're trying to like get the word.
Because she was like,
Where, what is
She's just like so smart, but she's always too little.
she's a pharmacist. She's worked like pharmacist for a while.
That's
So you kind of just pick up the basics.
this folder is what kept.
He's coming around.
let's ask this. That's how we got this. That's how we got
This might be one of this one. Minus this. Which is all everything of it.
I don't know how to feel about it. I picked
Question is right here, if I can get right to the correct answer, is at least one
Well, he also just said to not simplify. So,
unless you get all these things. That's in the first sense.
especially if it's on his own.
As far as the stuff, but there's a.
Yeah.
We did, so it's first of all.
Josh is like,
That's among us. You have to leave us.
Josh, this is your first time taking this class too, right? We have to say the yuppies. But it was class alphabet.
So you know the difference between
I've learned this.
That's exactly
Yeah,
what
no,
I
that's exactly what, yeah. You just have to do it
You have to be.
it's so much by repetition. That's why plus
Or e to the x times x squared.
Oh, I see what you're doing.
Yeah.
Okay. Okay, yeah, that makes sense. Yeah, we had the same thing. Yeah.
Yes, we all either got it right or we all either.
111 is just
We all got it wrong.
that's going to be statistically. We're not sure. So every single one of us does that gets because it gets more focused. Okay.
But then where do we go from that? Or is that as simplified as you want us to touch?
I mean, that's the derivative, so I think that's your first hurdle that we want to focus on. But yeah, you could simplify. Usually simplifying just involves taking out the greatest common factor and then going from there. So you could take out a 2 e to the x negative 1/2. Right.
Never.
So does that explain?
That's what we're doing. For how many electrons?
You take out a 2 e to the x. And then you
Like you're dividing additional elements. Then from there how many electrons does that have? Oh, with the addition of half. After that, then you have power. Did you know Lewis then? That's what it's called. No, I thought you said Lewis dot. No, Lewis. Yeah, just Lewis structure. That's all. My teachers apparently
I need to make sure I get you a birthday drawing today.
I'm thinking of what I want to do. I think I have a good one.
It has to be after break. Look how cool this picture is.
And she likes my
I don't want that tattoo.
something fun. She's cool about it. Like something nice.
Collector's edition. I'm excited.
Oh, wait, no,
Pretty. It's absolutely. So in terms of
I am a collection.
Oh,
I tried to get that top hook. Cool. What am I going to do after this today?
So, okay, so when you get invited, like say you have 2x and 5. Yes. You have to know the equation. So we're subtracting negative 1/2.
I'm too chubby to run myself. I also don't have my headphones.
All of this shit.
I have my headphones with me. That's fair. I need to start bringing my, because I have big headphones. I also really want to get a new pair of workout shoes. So I'm going to tell myself after 50 workouts. I need to buy myself a pair. Because I don't want to buy a that I don't wear.
That's fine.
No one can make fun of me for how unfit I am.
The one comes from this side.
But it kind of makes sense. I don't know. My doctor was like, going to the gym will cure your depression. I was like, all right, let's go. Bet.
Right.
At first he was like, here's the meds.
Yeah, here's some medication. And I was like,
No.
I'd rather not. And he's like, all right, go to the gym. It's like, really? That's fine.
I'm depressed at the gym now.
Depressed while sweating.
I'm out.
I went to like Dolls and stuff, brand new, you know, sorry to get into it. And immediately first step he tried to prescribe me, and I was like, okay, let's hold it back a second. Because this would be my first time taking medication.
All right, I think initially this is what you want to aim for. Just we're getting the hang of the product rule.
Is that the final answer?
Well, I mean, we could combine the 4 and the 1/2 here. But yeah, I mean, on the exam, if you wrote that as the derivative, I would be fine with that.
What if you separate, like, I rearranged the original equation? moved
Okay.
4
Oh, he doesn't.
to the far right, so that way I could
Oh, yeah,
isolate
he doesn't multiply
e to
that.
the
Yeah.
x to keep it e to the x.
Where did he get the 4 from?
Right, you could do that.
He was
So mine was
Yeah.
4e to the x times square root of x plus e to the x times 2x to the minus 1/2.
Yeah.
Negative 1/2.
Yeah, that's fine.
Okay.
Yeah. So yeah, depending on how you wrote it, like some people said, well, you know, the function consists of a constant times one function of x times the second function of x. So the constant times the function of x can be pulled out. And just take the 4 out and call your first e to the x and second root x and take the product rule of that. And then multiply your 4 in. It's all the same. Because notice from here, this is not how we would go to simplify it, but if I had the 4 out front of the entire derivative, then I would have this. Right? If I just left the 4 out before I took the derivative using the product rule, you would just have that 4 out front, which just is equivalent at this step here of factoring the 4 out. You know, so it's all the same thing. And really, you know, if we're working on simplifying this, we have the 4 times the 1/2. 4e to the x to the 1/2. You know, so that's also acceptable as the derivative. Greatest common factor is 2e to the x times x to the negative 1/2. So you could have factored that out if you were feeling ambitious.
Is it okay to leave that positive 1/2, that x to the positive 1/2, to leave that as square root of x?
Yeah, and again, somebody could have this as 1 over 2 root x. You could have this represented as root x.
Okay, so
Yeah.
there's not like one way that's firmly
No.
representable?
No, so we could have this, as long as you can get to this step, however you represent your exponents as radicals or whatever, it's totally fine.
Okay.
But see, somebody could have this representation or the root in there, or somebody could have this representation or the root in there, or somebody could have the bottom representation or the roots in there. So, you know, there's kind of like 6 different ways to represent this, depending on how you write it. The main idea is this, what we've started here, because that's the derivative. Yeah.
So perfectly fine if you use any one of those.
Yes. Exactly, yeah. And really on the exam, if I said find the derivative, do not simplify, then this is the step that you're looking at right here. Yeah. But you want to be able to get it down to this bottom line eventually. So you still want to be familiar with how to do that, but right now we're focusing just on the derivative itself. Okay. Do y'all have any questions on that example?
How does that power distribute to the positive half on the side?
On this step right here? Yeah. So the negative, x to the negative 1/2 times x to the first, you add their exponents.
Negative 1/2 plus 1.
Yeah. Okay, I don't know what this was. I don't know what it's doing.
Yeah, I don't know what that was either.
X to the 1.
Really just messed us all up.
It's like the ramblings of a madman.
It's in your handwriting.
It is my handwriting. Couldn't tell you what I was doing. Oh yeah, here's that first term we simplified. You know, I don't know. I think a lot of people have a hard time. Not a lot of people, but some people have a hard time seeing this thing right here as the product of 4 different things. 4 times e to the x times 1/2 times, right? So then the order of how we write that comes into question. How do you want us to write that? And the answer is it doesn't matter because you're just multiplying 4 things together. A times B times C times D is D times A times C times B, right? Doesn't matter how you order your multiplication. So I think that's all that was. Anyways. Okay. You know, just ignore it.
Okay.
It does pertain to this question though. Are there any other questions? Yeah.
How are we left with 2x and not just 2?
So you just add the exponents. Like if I redistributed the x to the negative 1/2 in, I have 2x to the first times x to the negative 1/2, and 1 minus 1/2 gives me a positive 1/2.
Okay.
Yeah, it's weird because I don't think in prior classes you do a lot of factoring out of negative exponents, but the idea is still the same.
I feel like in previous classes, I don't even remember simplifying that heavily before.
Yeah.
Like, at all.
Right. You probably got it compartmental. It was all compartmentalized, and now here it's like, oh hey, you have to do all of it.
Yeah. All of the equations weren't nearly as heavy
Right.
to simplify,
Yeah.
factor out, etc.
Agreed. They weren't as complex.
Yeah.
I'll agree with that. But do you have the ability to do it? Yeah. You all should have the ability to do it for sure.
Thanks for believing.
I believe in my own ability. I gotta believe in yours, right? I just have years more practice. That's the only thing that separates me from you. It's not that I'm smarter than you. I promise.
Multiple years of practice.
Yeah, but it's not that I'm smarter. All right.
I think I never still like I came up with a new joke. I told my off of he was crying. I could hear him crying.
All right then. Time for the quotient rules. You should, really you should look at these 2 rules at some point today, just to reinforce how to take the derivative of a product and quotient. So here we see the derivative of a quotient, f divided by g, is g f prime minus f g prime all over g squared. The other, I think there's like 2 typical ways that people remember this, is to think about is to refer to the top function as high and the bottom function is low. So the derivative of the quotient then is low d high minus high d low all over low squared.
Now, since this is negative, is the order crucial here?
Yeah. The order is crucial.
Okay.
Because the negative one is the top times the derivative of the bottom. That one has to be negative according to this formula.
So like a final minus initial, like the low minus high.
Well, yeah, maybe if you want to think of it that way.
They're at least building from the same premise.
Yeah. Or just calling the top function, the numerator the top, and the denominator the bottom. The quotient rule says take the bottom function and multiply that by the derivative of the top, minus the top times the derivative of the bottom, all over the bottom squared. So however you choose to remember that, again, the important piece here, outside of the formula as a whole, is that that second term, the f g prime, that has to have a -1 multiplied through, because that's the -1. Okay, let me see what we have. Does anyone have any questions about that? We actually didn't derive the product rule, and so we didn't derive the quotient rule either. But once you have the product rule established, then you can, with the limit process, then you can establish the quotient rule through like this algebraic process. But just as a reminder, when we looked at the quotient rule, or the product rule rather, if we said to find the derivative of a product, f times g, I'll go ahead and write it out in full. Initially, how that's justified is you have to compute the limit as h approaches 0. F x plus h times g x plus h minus f of x times g of x all over h. So in order to justify the product rule, if you look in your textbook, they go through how do you compute that limit, and how does that limit actually come out to be f prime g plus g prime f. And then once you've done that, you can justify the quotient rule sort of in an algebraic way. For example, we've a rational function here, x plus 1 over x plus 2. Find the derivative of f of x. So we hopefully clearly see f of x consists of a quotient. So to take the derivative, we have to use the quotient rule. So we take the bottom function times the derivative of the top. And again, I'm just going to write down every time I say derivative instead of just computing the derivative. Bottom times the derivative of the top minus the top times the derivative of the bottom. All of that's over the bottom function squared. So the vast majority of times when you're computing the quotient rule, or the derivative rather, using the quotient rule, we just leave the denominator squared. We don't worry about expanding the denominator. So you have to piece it together that way. Otherwise, you're not taking the derivative of the quotient. We have x plus 2. The derivative of x plus 1. The derivative of x plus 1 is just 1. Minus the quantity x plus 1 times the derivative of x plus 2. Again, that's just 1. All of that's over x plus 2 squared. So we can simplify this. It's pretty straightforward to simplify the numerator. Does anyone have any questions on that? The application of the quotient rule? Okay. So it's worth pointing out again that it's minus the top times the derivative of the bottom. Whatever you get as a whole, top times the derivative of the bottom, all of that stuff is multiplied by -1. It's just not a piece of it, right? The whole thing is multiplied by -1. So it's important to keep these parentheses here, even if you have to, if you have something a little bit more complex over here, put another set of parentheses around it. But everything over there needs to be multiplied by that -1. So we have x plus 2 minus x minus 1 on the top. So the x's cancel out. 2 minus 1 is just 1, and then we'll leave the denominator alone. So that's our derivative.
How'd you get the one in the numerator?
Yeah, the numerator here, we just have the x plus 2 times 1. So that's just x plus 2.
Right.
And then we have the negative distributed to the x and to the 1. So that's negative x minus 1.
Okay.
Which is equal to 1.
Then x wouldn't be able to equal -2 in this situation.
Right, notice the derivative is not defined when x is -2. If we look at the original function, it makes total sense because the original function was not defined at x equals -2. So our rational function here, when we say x can't be -2, on the graph of the function f, what's happening at -2?
An asymptote.
You have a vertical asymptote, right? So we would expect that if we find the derivative, and we said, well, the derivative tells us the slope of the tangent line at all points on f of x, we would expect that the derivative would also not be defined at -2, because on the function you have a vertical asymptote. So if I said find the slope of the tangent line at the vertical asymptote, you can't do that. So our function originally was undefined at -2. We see that carry on with the derivative as well. So you see that, I guess, even more generally here with the theorem where it's f divided by g. Well, f divided by g is not defined when g is equal to 0, right? So the original function is not defined when g is 0, but it's also true for the derivative. Derivative is not defined when g is 0 either. Okay, yeah. Any other questions on this? So let me back up. Now if we look at, like, take the derivative of 1 over x squared. Well, I guess there's two ways we can take the derivative. We can say, well, that's as it is, it's a quotient. So if I take the quotient and apply the quotient rule to find the derivative, I'm going to say it's the bottom times the derivative of the top minus the top times the derivative of the bottom, and then put all of that over the bottom function squared. Okay, so the derivative here of 1 is 0, so 0 times x squared is 0. We have -1 times the derivative of x squared, so we have -2x all over x to the 4th for our bottom, which simplifies to -2 over x cubed. So now I guess we have a different way of looking at here, particularly negative exponents. What else we could do, we could just say, or if I'm asked to take the derivative of 1 over x squared, before I take the derivative of that function, I'm just going to rewrite it as x to the -2. And then just use the power rule for that. So -2x to the -3 is equal to -2 over x to the +3. So anyways, just to show you that those things are consistent. It's obviously more efficient to write it as a power of x than it is to go through the quotient rule. But if it's overlooked and you see that as a quotient, there's nothing wrong with applying the quotient rule. Any questions on that? Okay, so find the derivative of x squared e to the x over x squared plus 1. So what's the overall structure of this function is what? It's a quotient, right? Don't pick at little pieces of the function before you take the derivative, because if I look at this function and I say, well, I'm overwhelmed because I see a product in the top and just a function on the bottom, right? So we have to look at the overall structure of the function to determine what derivative rule do we apply first. Since this function consists of a quotient, then we have to apply the quotient rule first. You can't just take the product rule on top, right? So we have to apply the quotient rule to take the derivative. And I think in this example in particular, the benefit of adding, writing out the derivative explicitly as you say it is going to become evident. So the quotient, the bottom function, times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So we applied the quotient rule because the function was a quotient. If any other derivatives show up in that rule, then that's fine. We'll take them off to the side and treat it almost like a completely separate problem. So now we're going to take this thing off to the side, down below, wherever you have room. We need to compute that derivative, because whatever it is, we've got to put it in place of this derivative here, right? Is everybody all right with what we're doing, where we're going? Okay, so let's address that separately. We're going to find the derivative of x squared e to the x, and then that's when we can focus on the individual components of the function. That is now a product rule. So we have the first times the derivative of the second plus the second times the derivative of the first. So other derivatives present, and to go ahead and compute that. X squared e to the x. Derivative of x squared is 2x, and we have our e to the x. So there's the derivative of that product. So that's like, that's an aside piece to our main problem. So we're going to take that, x squared e to the x, 2x e to the x, and plug that back in for this derivative here. So times that derivative, which was x squared e to the x, plus 2x e to the x. Minus x squared e to the x times the derivative of x squared. So that's times 2x. Then all of that's still over x squared plus 1 squared. So we're going to stop there because we don't have any other derivatives showing up that we have to compute, right? When we wrote all of this stuff down, we never said derivative, or we never, said to ourselves, there's a derivative in there. So that at this point, we're done with taking derivatives. So this is our unsimplified version. This is the derivative of f. Do y'all have any questions on where we're at? Does that make sense?
Can you elaborate on the derivative of x squared e to the x?
Yeah, so that came up as, that was the bottom times the derivative of the top.
Right.
So we wrote that out explicitly because now we know that the derivative is not done. I still have to compute this derivative and that derivative over there. But so then we took this derivative off to the side and said, what is that derivative? So that function, or that piece of our function rather, is a function of x times another function of x. So we said to compute that derivative, we have to use the product rule.
Okay, so for that we have to...
Yeah, so this is, that's our product rule. Again, other derivatives showed up. We cleared those out by taking the derivative. So that's what we ended up with, and that had to go in place of that other derivative. So that goes in place of that derivative right there, to this one. So I think a lot of these, especially that are more complex, I guess is the word, you will be computing derivatives off to the side or down below because they're sort of like secondary computations. So we've got those out of the way. And I'll just note here, this, like if I told you to find the derivative of this function and not simplify it, that's okay. That's where you want to stop on the exam. That's totally fine to leave it right there. If the instructions say not to simplify, that's fine. You don't want to say something is the derivative that has derivatives still left to take. That's pretty much how you know when you're done. Okay. I mean, we can simplify the top, but I think we're just going to leave it like that since we're just trying to get the feel of how to take derivatives at this point. Sorry, this is, not to mislead you, but this is x squared plus 1 times that derivative. So that x squared plus 1 would actually be distributed to both x squared e to the x and 2x e to the x. Okay, any other questions on this? All right. So again, that function that we have here, that for any given x represents the slope of the tangent line on the given function, x squared e to the x over x squared plus 1. All right. Everybody all right? Moving on. This is from your homework. I do, similar to the one we just did, I do want to skip that one. If you have problems with that in your homework, then I'm happy to do that in class. We keep moving. So here's an actual application. We're given the population of cells given by P of t, where T is in hours and P of t is in millions. So question A says compute the instantaneous population growth rate for t larger than or equal to 0 and identify the units. So what does that mean I'm going to do here when I see compute the instantaneous population growth rate?
Find the derivative.
Right, so there's instantaneous rate that's associated with our derivative. So it says find p prime of t, and then describe the units associated with p prime of t. So the population function is another quotient, so we have the quotient rule, the bottom times the derivative of the top. Oops. Derivative with respect to t. Bottom derivative of the top minus the top times the derivative of the bottom. All over the bottom squared. Shoot. So we have the derivative of 400 t. It's the derivative of 400 t. Yeah, you can split it up. It's a constant times a function of t. The derivative of t is 1 times the 400 that we pulled out. Derivative of 400t is 400. And derivative of t plus 3 is 1. So we could work on simplifying this, which I think we should because it's not terribly difficult. Notice both of these terms in our numerator, we could just take that 400 out. So I'll write that over here. So we factor out the 400 from the top, and then we have t plus 3 minus t left over. So the top is just 400 times 3. We have 1200 over t plus 3 squared for p prime. So then what are the units for the derivative p prime? What is a derivative in general, in a math sense? It's the slope of the tangent line. So a derivative represents a specific kind of slope. And a slope is measured how? From an algebraic perspective. Rise over run, yeah. What's rise? It's the change in y, and the run is the change in x, right? So remember this notation for the derivative, where we said the derivative could be identified as dy over dx. It's just a tiny change in y over a tiny change in x. So the units of your derivative will always have the x units, or the y units rather, divided by the x units. The y units here correspond to our population in millions, and the units for x, if you will, are time units. So, I don't know if this is helpful to think about p prime as the derivative of the population with respect to time. And then you explicitly see what that is, right? It's just a small change in population over a small change in time. So the units are million. Well, I guess cells, millions of cells, whatever that was, I think, cells per hour. Isn't that hours?
Yeah.
Okay. So if, like, let's just say you ended up with a derivative that you plugged a t value in, and you get 10 out of the derivative. How do you interpret 10 as p prime of some value?
10 million cells per hour.
10 million cells per hour. Is that a decrease or is that an increase in cells? It's increasing because you have 10 million. It's not negative 10 million, right? So like a positive number out of the derivative would indicate how many cells per, how many millions of cells per hour that you gained at that very instant. And a negative number out of your derivative, it would indicate how many millions of cells you lost per hour at that particular instant.
It wouldn't be possible to get a negative number out of this function though, right?
Yeah, no, it's not possible to get a negative number. The denominator is always positive, and so is the numerator. But that's the idea. If I want to know at time equals to 2.357 hours, how much was that cell? How much was that population rather increasing? How many cells were produced at that very moment in time? Is outputted by p prime of t.
How did you arrive at the derivative of p over the derivative of t?
So that's just the alternative notation for p prime.
Okay.
Remember the alternative notation for f prime was df over dx or dy over dx, because y was f.
Okay.
Yeah. So yeah, that's just another way to notate derivative. Okay. So we haven't talked about steady state population. It does come up in your homework, so please make sure that you take note of what steady state population is, because I get a lot of emails about what is steady state population. So we're going to address it right here. Steady state population has to do with the population function, not the population growth function that we just found. So steady state population is just, it's just really you're answering the question based on the population of this whatever I'm measuring. Does it actually ever level off? Does it reach a steady state where the population is not increasing and the population is not decreasing? So to answer that, we have to answer the question, what is the limit as t approaches infinity on the population function p of t?
That's essentially also just asking when the tangent line is horizontal, right?
No, when the tangent line is horizontal is when p prime is equal to 0. So when is the instantaneous growth rate 0? That's where you have a horizontal tangent line. What this is saying, it says, okay, the population, as time progresses indefinitely, what happens to the population?
It's steady state population, so is that essentially something for the asymptote?
Yeah, that's the end behavior. What is the end behavior of your population function? Does, like, I don't know, probably every other species but humans, their population is going to look like this, right? You start off with some population, and then they reproduce, and then they reproduce, but eventually they're gonna flatten off. Maybe even the population decreases after it levels off. It might start to decrease, like introduction of more predators or something. I don't know. So that would be a steady state population if that population leveled off. For us, our population is more like this. It's something like that, right? But there is no steady state reached by that second graph, because it just keeps going and going. So that's all they mean by steady state population, is basically you're asking the question, does the population ever level off? we're going to compute the limit as t approaches infinity on our population function. Which was this. And what's the limit at infinity on 400t over t plus 3?
Infinity.
Infinity? Does anyone disagree?
I disagree.
You disagree? Anybody else? How can we disagree?
I think it's 400, isn't it?
Is it 400 or is it infinity? In terms of t, this is a rational function, right? Limits at infinity are computed by looking at leading terms. So as far as computing the limit at infinity, this is equivalent to 400t over t, which is equivalent to 400. Right, so what's the limit as t approaches infinity of 400?
400.
It's 400. So what does that mean?
The steady state population is 400.
Yes, steady state population is 400 million cells. So therefore, steady state population is 400 million cells. Just in a math context, that function, p of t, 400t over t plus 3, has a horizontal asymptote at y equals to 400. Now, it should be like really obvious if we looked at the graph of the population function. I have to get way out here. Okay, so here's our population function. Of course, we're starting our watch. We're measuring that growth at time equals to 0. So we'll just show it for that. So there's our population function. You see, the population is increasing this whole time, but as we get further and further out, you can see that it's flattening off. And there's our asymptote, which corresponds to the steady state population. Okay, what time is the instantaneous growth rate the greatest?
It's going to be as close to 0 as you can be without being 0.
Okay. Yeah, so there's two ways to answer this. So let's just list those. One way to answer this is to look at what, or is to do what? What time is the instantaneous growth rate the greatest? How can we answer that question?
Would you put that like isolate t in your plus coming from the right back towards 0?
Like a limit? Is that what you're? Yeah. So the limit would just say, like, as we get closer and closer to a certain value, what does the function get closer and closer to?
Right. But I don't know. I'm trying to think of what you put it. Because the closer to 0 is going to be the greatest growth, right?
Yeah. So, but how do we know? Like, how would I know that closer to 0 is the greater growth?
Could you just get derivative? Instantaneous growth rate and equal it to 400, because you know that's what the population, or that's what the, it's 400 million is our steady state. So if we know that's the highest, that should also be when the growth rate is the greatest, right?
No, not necessarily, because if you think about that population function out towards the very end, what is the growth?
Very much.
It's pretty much nothing, right? In order for a population to reach a steady state, that population has to quit increasing or decreasing at a certain time, right? So the question isn't asking us about this graph, because this graph was our population function. I think it's important to know that the question is asking what time is the instantaneous growth rate, the derivative p prime of t. At what time is the growth rate the greatest? Not population is the greatest. So you alluded to just somewhere close to 0 because why?
Because that's when the slope's the greatest.
Because when the slope is the greatest, right? So if we look back at that population, remember at any point on this population function, that's the instantaneous growth rate, the slope of that line. So we can say, well, on the population function, when is that slope the greatest? Does that make sense? Because as long as we're talking about the slope of the population curve, we're talking about its derivative. So we can just try to eyeball it and say, in my opinion, it looks like the slope of that curve is the greatest here in some region, right? So like in my opinion, maybe the slope of that curve is greatest somewhere in between time equals to 0 and time equals to 3/2, right?
Is there something we could set the derivative to? It's like, because, if we set the derivative to something specific, we're setting it to that slope.
Right.
But I don't know what you would actually set it to.
Yeah, so let's address that after we address this. So one way to answer this question is to look for on the population function p of t, the highest slope. Or if you want to think of it as steepest, that's fine. Highest, greatest, whatever. So again, on the population function, you put your pencil on there and say, well, at what time is the slope of that the greatest? Is it here? It's definitely not here. Could be here, could be here, right? So this is just an approximation, is the best we can do with just looking at it, right? So that would be an approach that wouldn't give you a very accurate result. And I don't know, maybe it's a trick question, because in order to answer when the population growth rate is the greatest, like, just think about this function for a moment. What if that were the population growth function? And I said, maybe it would stop there. If that were the population growth rate function, and I said, when is that population growth rate the maximum? It's pretty easy to answer that question, right? You say, well, my population growth function is just some quadratic, whatever. Oops, that's x, right? And then you could say, well, how do I find the maximum of a quadratic? I just find its vertex, right? If this were something more complex, like a function like this, how do you find the maximum there? We've yet to talk about how you find maximums of functions, right? But we have alluded to it, specifically with functions like this. How do we find these peaks and troughs?
You set the derivative to 0.
Right.
See what pops out.
That's where the slope of the tangent line is 0. That's where the slope of the tangent line is 0. So the process of finding where any particular function has a maximum involves looking at its derivative. We haven't talked about that yet, so we can't really take that approach. So the other one, I mean, like I said, maybe it was a trick question, but the other one is just graph P prime, the growth rate, and look for the highest point. For now, that's the best way, that is the best way to answer that question. So where is the instantaneous growth rate the greatest? I don't know, but I know what the instantaneous growth rate function is. Yeah.
So you set it to 0 to get a horizontal tangent. Would you set it to infinity to get a vertical tangent, if there would be one? Would that give you the...
So the idea of where you would have a vertical tangent would more than likely be really obvious from the derivative itself. So like if this were my derivative, the derivative is undefined here. So, you know, you just kind of ignore the fact that this is a derivative for the moment and say from an algebraic perspective, this function would have a vertical asymptote at 0. Well, since this describes the derivative, I would say I've got a vertical derivative, a vertical tangent at x equals to 0.
Okay.
So, yeah. All right, so we'll look at the graph of the, we'll turn this off. We'll graph the derivative. Is that it? That was it. So we're only showing that for positive time, so we'll restrict that to. So we say there's my population growth rate function. The highest value occurs here at 0. Let's make sure we're looking at that. Yeah. So that's the highest value on the derivative is at time equal to 0. So the population of cells, that means initially, as soon as we start watching them, initially they're reproducing, I guess, at the fastest rate. So then to answer that question, we would just say, when is the instantaneous growth rate the greatest? The instantaneous growth rate is the greatest at t equals to 0. You know, by the time the exam rolls around, you would be able to find this without having to graph it. It's just for now we have to graph. Does anyone have any questions on that? I think there's one more piece. So part D, if the limit as p prime of t, as t approaches infinity on p prime of t is equal to 0, what does that mean? How do we interpret that?
The population growth is almost negligible.
Yeah.
It's not very top drops to almost 0.
So remember, p prime of t describes not the population, but the instantaneous growth rate of the population at any time. And we're saying that as time progresses, the growth rate of that population is getting closer and closer to 0. Let's just write that out. Growth rate is 0. Okay, so that as time progresses, the growth rate's 0. What does that mean about the population?
It's decreasing.
So,
It's becoming static.
right, it doesn't necessarily imply that it's decreasing, right? At some point, we see the population decreasing,
Sterilized.
but it just becomes stagnant, right? It just says at some time, eventually, the population of the cells quits growing, and it doesn't actually, not only does it say that it quits growing, but it also says that there is no gain or no loss, right? The growth rate is 0, there is no gain or loss in population. So is that's consistent with what we said about the steady state. In order to, the other interpretation of a steady state is that in order to reach a steady state, the growth rate of that population has to stop growing. It has to stop increasing and decreasing, right? Because if the population like grew to 400 million and then it started tapering off, we wouldn't have said there was a steady state there, right? Because it doesn't actually level off. So we can relate this question back to the steady state question. I guess it's time to go.
So that's where it's an equilibrium point.
Yeah, right.
Between gain and loss.
Yeah.
So basically, it's like approaching 400, the growth, it's as the population.
I don't understand why people
the
think
growth rate is approaching zero.
Yeah.
Yeah.
Yeah, you see that right here too, right?
You're like,
Yeah, so that's the derivative there.
See, everyone,
Caught up to the speed of things.
everyone thinks it's gross.
Well, if you